All right, hello everyone. So this video is going to go through the group challenge on the rigid rotator wave functions that we did in class, our very last class meeting. So if you'll remember, our rigid rotator wave functions have this interesting form. We call them Y instead of psi. So they are spherical harmonic wave functions or rigid rotator wave functions, where L and M are the two different quantum numbers. And they have this interesting form, very similar to our harmonic oscillator, right? They've got a normalization constant, which changes every time you change quantum numbers, times this Legendre polynomial p, which is always a function of cosine theta, and then an exponential term at the end as well. And so let's start with the normalization constant. This very first question, or first two questions really of the group challenge, asked you to write out two specific spherical harmonic wave functions. So let's look at what the normalization constant looks like just to remind ourselves. So it's this 2L plus m over 4 pi times L minus the absolute value of m factorial L plus the absolute value of m factorial, all square rooted. So we've got some interesting fun factorials coming your way. All right, and because we're going to need them later, I'm going to go ahead and provide you with P11, which has an equal sign, which is sine theta, and P21, which is 3 cosine theta sine theta. So these are the two Legendre polynomials that we're going to end up needing to solve this group challenge. So question 1 asks you to solve for y, the wave function y, when L is equal to 1 and m is negative 1. So let's start by looking at our normalization constant and figuring out our normalization constant. So we've got L is 1, m is negative 1. So if we plug those in, we're going to end up with 2 times 1 plus 1 over 4 pi times 1 minus 1 factorial, or 0 factorial, over 1 plus 1 factorial, or 2 factorial. So remember, factorials are whatever number you have times the number below all the way down to 1. 0 factorial is always defined as 1. So we have 3 over 4 pi times really 1 over 2 to the 1/2, or we could write that as 3 over 8 pi square root. Okay, so we have a normalization constant, so let's go ahead and plug our normalization constant in to our wave function. And we can erase this little piece of work and go ahead and start filling in our Legendre polynomial. So our Legendre polynomial, it doesn't matter that m is negative 1, because of the Legendre polynomial, m has an absolute value in it. So when m is 1 or m is negative 1, you'll get the same Legendre polynomial as long as your L is the same. So let's plug that in. So our 1, 1 Legendre polynomial is sine theta. And then our exponential is going to go to e to the negative I theta when we plug in negative 1 for m. Sorry, phi, negative I phi, when we plug in m equals negative 1. So we have solved number 1. Question 1 was just write out this wave function. So question 2 is do the same thing, but now L is 2 and m is 1. So again, we'll start with our normalization constant when L is 2 and m is 1. 2 times 2 plus 1 over 4 pi times 2 minus 1 factorial over 2 plus 1 factorial, all square rooted. So we can simplify this to be 5 over 4 pi over times 1 factorial over 3 factorial. 3 factorial is going to be 3 times 2 times 1, or 6. So we can simplify this to 5 over 24 pi to the 1/2, because 6 times 4 is 24. So let's go ahead and plug all that in as our normalization constant to our wave function. And then we need our Legendre polynomial, which for the case of L equals 2, absolute value of m equal 1 is 3 cosine theta sine theta. All right, and then we need our exponential term. So exponential term here is going to be e to the I phi, because m is positive 1. So congratulations, those are the first two. So now let's do something with those wave functions. So the next question asked you to show that these two wave functions that you've now written out and defined are orthogonal to one another. So remember, this is not orthonormal, just orthogonal. So we're not proving normality, we're only proving orthogonality, which means that their integral of these two wave functions should go to 0. But here's going to get a little more tricky because we're going to have to use a double integral. So I've written back up the two wave functions just to remind you where we're going here. So we're looking for this integral. Phi is going to be integrated from 0 to 2 pi. Theta is going to be integrated from 0 to pi. And we're going to arbitrarily choose y1 negative 1 to be complex conjugate and y21 to be the wave function by itself. We could go in the other order. We should get the same answer. Remember that our integrand here is sine theta d theta d phi. All right. So we're going to go ahead and keep on going. Let me see if I can actually erase that real quick. All right. So let's go ahead and continue through this integral. We've got, if we plug in our complex conjugate, we're going to get our normalization constant for y1 negative 1 sine theta. Our exponential term is the only one actually affected by taking the complex conjugate. Instead of having negative I phi, it's going to be e to the positive I phi. And then we'll go ahead and plug in our normalization constant for the second wave function. Our Legendre polynomial and our exponential stay the same. And then our integrand, of course, is still sine theta d phi. So when we continue to work this out, we can pull all of our constants out front. And I really didn't combine them. We could combine them, but I've decided that we're going to leave them just as they are. So if we combine those, and then we can come inside our integral. And let's combine all of our theta terms. So we're going to end up with cosine theta sine cubed theta, because notice that we have sine theta times sine theta times sine theta, right? So sine cubed theta. And then if we combine our phi terms here, we've got e to the positive I phi times e to the positive I phi, or e to the 2 I phi when we multiply them together. And then the remainder of our integrand is still d theta d phi. So we're going to call all those constants out front c, because as all of you know, I'm not very patient about that. So that's all just constant c. And then we need to know what the integral is of cosine theta sine cubed theta. And it turns out that that's going to be 1/4 sine to the 4th theta. And then we're going to need to plug in our bounds. So we have all of our constants. We still have this integral over phi from 0 to 2 pi, 1/4 sine to the 4th theta, evaluated from 0 to pi d phi. So let's go ahead and plug in those bounds. So sine to the 4th pi is equal to 0, because sine of pi is 0. 0 to the 4th power is still 0. If we plug in 0, sine to the 4th of 0 is also equal to 0. So 0 minus 0 is still 0. And so if we plug that into our integral, we're going to get 0, right, c over 4, our integral of 0 times d phi. And the integral of 0 is simply just 0, right? If we multiply by 0, we still get 0. So we've now proven that these two wave functions are truly orthogonal. All right, so this group challenge had one more question on it, and it was to find the average value of the angle phi for only the first wave function. So the wave function y when L is 1 and n is negative 1. So how do we go about thinking through an average or an expectation value? So first off, let's write out our wave function, just so we have it here on the screen. So it's the same wave function that we've been playing with. When we define our average value, we have to still do a double integral because we're in spherical coordinates here. R is still remaining constant, so it isn't a triple integral. But our definition of average value is complex conjugate of our wave function. Then we have an operator for our Hermitian operator that corresponds to that value, which operates only on the original wave function. Once we operate on that original wave function, then we multiply by the complex conjugate, and then we'll do our integration. So what is the average value, or what is the operator associated with phi? Well, phi is just an angle, and angles are types of positions. So just like it was for our x positions, it's simply multiplied by the angle phi. So that's kind of nice. All right, so let's do this integral. Let's start plugging things in. So we still have our bounds. We'll plug in our wave function. Remember, when we take the complex conjugate, the only part that changes is that exponential. So instead of negative I phi, it becomes positive I phi. Multiply by our operator, which is just in this case multiply by phi. And then we have our original wave function, and then our integrand, which is sine theta d phi. Okay, so let's combine some like terms. We can bring the constant out front, so we've got 3 over 8 pi square root times itself, so just 3 over 8 pi that comes out front. And then let's combine our theta terms. So we still have 3 signs. We don't have a cosine in this one, so just sine times sine times sine, or sine cubed theta. And then we have phi e to the 0, because we have e to the positive I phi times e to the minus I phi. When we add the exponential terms together, right, so we're multiplying these exponential functions together, which is really the same as adding the exponent part. Since they have the same base, we're going to get e to the 0, and e to the 0 is 1. So we can ignore that, d theta, d phi. So let's start with sine cubed theta. So we need to know what the integral of sine cubed theta is. And so I'm writing that, providing that for you. It's negative 1/3 cosine theta times sine squared theta plus 2. It's kind of an interesting one. So we still have our constant out front. We're still going to integrate from 0 to 2 pi for phi. And then we've got negative 1/3 cosine theta, sine squared theta plus 2. And we need to evaluate from 0 to pi before we do our phi integral. So let's start by plugging in pi. Cosine of pi is negative 1. Sine squared of pi is 0. But then we're going to add 2 to that. So we really have negative 1 times 2, or negative 2. And then cosine of 0 is positive 1. Sine squared of 0 is still 0, but we're going to add 2. So we really have 1 times 2, or positive 2. So negative 2 minus positive 2 gives us a negative 4. So this whole integral is negative 4 times negative 1/3, or 4/3. So we can bring the 4/3 out of the integral. And we still have phi d phi, so we can go ahead and cross out our 3's, right? We've got 3 divided by 3 now on the outside. We also have 4 over 4 pi, so we can change this to 1 over 2 pi. And then we're left integrating phi d phi from 0 to 2 pi. Well, the integral of phi d phi is just 1/2 phi squared evaluated from 0 to 2 pi. So we can plug all of that in. We can combine our 1/2 and our 1 over 2 pi to get 1 over 4 pi. When we plug in 2 pi squared, we're going to get 4 into phi squared, or 2 pi into phi squared. Sorry, we'll get 4 pi squared. We plug in 0, we'll get 0. We can combine these. 4 pi squared over 4 pi, just pi. Well, that's kind of interesting. We got pi. Does that make sense? The second part of my question was, does this make sense? So let's draw our spherical coordinates. So remember, we've got here our coordinate planes z, y, and x. So let's say the purple dot is where we're going. R is fixed here, so the length from the origin is r. The angle coming down from vertical, the tilt from vertical, is theta. And if we were to draw the shadow or the projection of the line onto the xy plane, the angle from the x plane, or from the x axes in that plane, is phi. And phi is the one that can rotate all the way around. So theta can come down from vertical, going vertical toward the top to vertical toward the bottom. But phi can go all the way around, a full rotation. And so what this is saying is that we can go around half of a rotation. Phi can go around half, which if we think back to our particle in a box, the answer was the average position was halfway across the box, halfway across the length, or width if we were doing the second dimension. And if we think about our harmonic oscillator, the average value was equilibrium, or halfway, right? Not compressed or stretched, but equilibrium, halfway, which happened to be defined as 0 with harmonic oscillator. So this answer actually lines up really nicely with other answers we've gotten. And in fact, if we try to calculate the average phi angle for any spherical harmonic wave function, we should get pi. All right, so the next video I do for you will be on the hydrogen atom, so stay tuned. If you've got questions about this group challenge specifically, or rigid rotators, please add them to either the Slack channel, or you can email me, or you can add them to the discussion forum on Moodle that I'm going to attach. If you do email me, I would prefer that you use the other two methods actually, because it's really nice for you guys to see each other's questions. But if you really, really want to email me, that's fine. Please don't comment on the YouTube channel because I don't promise to check those comments. All right, thanks guys.